which is hosted by the SciLifeLab Data Centre, and it's called Using Containers to Simplify Machine Learning Training on Berzelius and Other Supercomputers. And this is a beginner-friendly introduction, so we assume that you have little or no knowledge about containers, and you probably haven't used a supercomputer or Berzelius before. So my name is Victor Sandström. I work as an AI data engineer at the SciLifeLab Data Centre, and me and my colleague Johan Alfredén will take you through this webinar, which will take approximately 1 hour, including questions. As extra support, we have Somi Chaki and Chuang Gu, who are both application experts at the National Supercompute Center. So if you have specific questions about Berzelius, we will probably redirect those questions to them. So this event is a part of an event series by the SciLifeLab Data Centre, and it's specifically aimed for life science researchers who use machine learning in their work. And we have an upcoming event, November 16th, which is about building and sharing machine learning applications within the life sciences. So this will be a practical tutorial and a workshop in Solna. We also have 2 other events planned where the dates are not set, and one is how you can track machine learning experiments using MLflow, and the other one is how to best organize data science projects. Now, if you have any ideas or want to help organize these events, please reach out, serve@sciliflab.sc. There's a code of conduct. I won't read through this, but basically says that be nice and use Zoom reactions or the chat if you like to say something. So some housekeeping, please stay on mute. Raise your hand if you want to say something. And this event is being recorded, so please switch off your camera if you do not wish to be visible on the recording. And last but not least, welcome to this event. So this webinar will be split into 2 parts. The first part, I will talk about some background concepts and examples. We'll briefly talk about Berzelius and other supercomputers. We will talk quickly about how you commonly work with these devices. And then we will dive deeper into containers, try to build some intuition for how they work. And we will do this by talking about them and then by doing a live demo where we'll start a couple of containers and try to see how they work and see if you can find a way to work with them yourselves and how they can simplify your personal workflows. And the second part, Johan will talk about how to train a machine learning model using first his local computer, and then we'll move over to Berzelius, and here he will show how containers will simplify the process of moving from his own laptop to Berzelius. And this will be a live demo as well. So we pray a bit to the tech gods that that everything works and that internet stays solid throughout. There's a GitHub repository where all the material in this event is stored. So if you need to find some information afterwards, you can just go to this GitHub repository. So don't focus too much on the specific details, try to understand the general ideas that we're presenting, and you can always find the exact syntax and stuff like that later. Okay, so about Berzelius and other supercomputers. So in general, a supercomputer is just a computer with really high performance compared to the machine that you probably have in your office or at home. And it generally consists of a bunch of compute nodes that are networked together into a cluster so that you can do parallel computations very efficiently. You get access to a lot of processors, a lot of memory, and a lot of GPUs. Now, these devices are very expensive and they have a bunch of users. So there's some security restrictions. For instance, you don't have root access, meaning that you cannot install any software, you cannot change any system libraries or frameworks. And you're also limited in how much resources you can consume. here we talk about GPU hours. So if you buy, say, 100 GPU hours and you want to train your machine learning model on 10 GPUs, then you have 10 hours to do so, basically. So about Berzelius, it's a National Supercompute Center compute resource, and it's specifically designed for machine learning, so training large neural networks on large data sets. It consists of 94 NVIDIA DGX A100 nodes, which is a machine learning computer with 8 GPUs, and this results in 752 GPUs in total. And I think they have between 40 and 80 gigabytes of memory. So compared to a gaming GPU that you perhaps have in your home computer, if you do machine learning or gaming, this has much more high performance. Berzelius has specific support for life science. So if you're a life science researcher and you want to start using Berzelius, or just curious about how to use Berzelius, please reach out to us and we will make sure that you get the support you need. So I won't go into that much detail how to get access to Berzelius, but basically it works. You apply for a project, and when that project gets approved, you get a user account. And then with that user account, you can SSH to Berzelius, provide a password and two-factor authentication. And when you do that, you actually end up in a login node. And from that login node, you ask for resources. So you access a GPU, for instance, by writing interactive -- GPUs equals 5, if you want 5 GPUs. And then you become assigned to a node on this cluster. We will work with Berzelius on this in this event, so keep this image in mind so you don't get too confused when we're in the login node and when we're on a compute node. So that's 2 different things. And you can find more information about Berzelius on the website seen here below. Okay, so a common workflow with supercomputers, since you pay for the amount of time you spend on the computer or how much resource you consume, you will tend to do as much as you can on your own devices. So you will maybe try different algorithms and tune for hyperparameters and train the model maybe on a small part of the data set if you have a large one. Basically, you will verify that the code works, you have no bugs, the model seems to be learning whatever you want to learn, and you have a solid piece of software. So then you're ready to move over to the supercomputer. So the naive approach would be to just copy the code, copy the data set, and then execute the code, run full-scale training on multiple GPUs. Are you guaranteed that this will work? Probably not, because I guess most of you have experienced the situation where you send code to a colleague or a friend, and they run the code and they get these weird errors that you haven't seen before. And when you fix these errors, then maybe some other project code breaks, and this interdependency between code makes software deployment pretty annoying. And this is where containers can be a solution for you. And I hope this will be clear later. So briefly about containers. I think it's important to do a shipping container analogy because it's related. Now I won't give you the full history of shipping containers. I don't know if I even know the full history, but basically you would produce something in a factory, and if you wanted to ship it across the ocean, there would be several steps where you had to repack, unload, offload, and repack the cargo depending on what kind of transportation device was being used or what kind of vehicle. And this made transportation very, very slow, unreliable, and expensive. So we invented the shipping container, which is a standardized unit of cargo, meaning that you can handle anything that fits inside a container in the same way. So it doesn't matter if you have a container filled with furniture and a container filled with bicycles. You will handle it in the same way. And with that in mind, you can then develop an infrastructure around handling these containers. So you develop these special cranes and special forklifts, and you make it possible to transport these containers on a train, on ships and trucks. And this infrastructure made handling containers or transporting goods very efficient, simple, and cheap. And it basically works the same way with software containers, or containers as I will call them from now on. So before we had containers, you had to install everything on your machine, and all the software that was running on your machine was interdependent somehow. There was no way to isolate them. And this made software deployment very slow and unreliable, and also pretty expensive, I guess. So we invented the container, which is a standardized unit of software, meaning that you have your code, you have all the dependencies, and you pack that neatly into a container, which can then be run on any compute environment that has this infrastructure of handling containers. And this made software deployment much more efficient and simple, and perhaps even more cheap, I'm not sure. So in the image here to the right is the official logo from Docker. And Docker is a tool for handling containers. And you can see that the shipping analogy is actually being used officially within this domain, so it's not my invention. But basically all you need is this tool to handle containers. This tool is called a container engine, or a container runtime. And there's a bunch of these. The most common one is probably Docker, as I mentioned before, but there's also something called Podman, and on Berzelius they use Apptainer and Enroot, and there are many more of these. There's of course some differences between these container engines, but they basically work in the same way, meaning that you have your infrastructure or your computer, which runs an operating system. And on top of that operating system, you have the container engine, maybe Docker. Then you use that container engine to start up containers. So the idea is pretty simple. So a specific example could be this. You're on Berzelius, which runs a Red Hat as an operating system. And on top of that, you have Apptainer. And then you use Apptainer to start a container that maybe runs Ubuntu with a specific version of Python and some version of PyTorch, or another container that runs Debian and has Java and Tomcat installed. Depends on what you want to do. But the nice thing is that if you enter the container, start using the terminal, it actually seems like you're running Ubuntu on Berzelius rather than Red Hat on Berzelius. And this is a nice thing that we will see later. And the benefit is if you are working perhaps with a laptop at home and you have a desktop in your office and you maybe work with Berzelius or some other computer, then you generally need to maintain 3 compute environments. So make sure that you have the same packages and same software on all 3 machines. But what you can do with a container is that you can just move this container between these 3 environments. And all you need to do then is maintain the container and not the 3 environments that you would otherwise need to maintain. And I think that's a real nice benefit. And I hope you will start use containers. So briefly, some terminology. You will see the word image being used later when we do the demo. And I don't want you to get too confused. It's a pretty confusing thing. But when you hear the word image, think of a container that is not running. So when you start an image, you get a container. Something like this. It's a bit simplified, but it's not that important to understand just yet. Okay, let's do some live demo. So let me just share a terminal like this. And I need to ask maybe Arnold, can you see my terminal?
Yes.
Perfect. So on my machine, I'm running Ubuntu and I have Docker installed. So let's write docker -- version. You can see that I have Docker of some version. It's not that important. So if you want to install Docker on your own machine, there's the official installer instructions are found on docker.com, which is the official website of Docker. But if we assume that we have Docker installed on our computer, let's just start by running a container. So you write docker run, Now, again, don't focus too much on the syntax here. Everything will be written down in the repository I mentioned before. That you write docker run, add some arguments, which are not important. And I want to start a container that maybe runs a different operating system than my own. So I'm running Ubuntu, but let's start a container that runs Alpine Linux. So I write docker run Alpine 3.18. Let's enter. Now it couldn't find this image. Think of an image as a container that is not running. Couldn't find the image on my computer. So it went to a container repository or a container warehouse where it found the image, downloaded it, and started the container. So now we're inside the container running the terminal. So let's see if we can see what operating system is being used here. All right, it seems to be running Alpine Linux of version 3.18.4. So that's nice. So inside this container, we can install stuff. So maybe on Alpine Linux, use APK as to install stuff. You write APK add, and let's install Vim, for instance. Vim is text software. This is just an example. You could install anything you like, basically some version of Python and then some R libraries or whatever. But let's install this Vim thing. Press enter, and now it's installed. So we can run it by saying Vim, and we can see that it seems to be working. Cool. So we exit the container. I'm back in my computer. Let's start another container. Maybe start one with Ubuntu 20.04. So same command, but just changed the image name. So I couldn't find it on my computer. So now it goes to the container repository. It downloads the image, starts the container. Now we're inside the container running the terminal. So let's do the same exercise. Let's see what operating system is being used. It seems to be running Ubuntu of a specific version that we specified. Great. Let me clear this for tidiness. And then on Ubuntu, you install stuff using apt, and you need to update the package list first. So let's do that. Now, again, this is just examples. So don't focus too much on the exact details I'm doing here. So apt install, let's install Vim again in this container. Here we go. We're done. Let's see if Vim works. Cool. It seems to be working. Great. So now we did that using two different operating systems, an Alpine Linux container and a Ubuntu container. Now let's use Vim to just create a test.txt file. I want to show you an important concept with containers. And inside this text file, we just write hello world. It's not important. And if we list all the files in the top level directory, or the directory that I'm in right now, you can see that we have the test.txt file store right here, which is as you would expect. But now if we kill the container and then we start it again, we list the same directory, you can see that the test.txt file is missing. So what's going on here? Well, a container is a fixed object, meaning that every time you run it, it will look the same, or it will be the same thing or the same environment popping up. So if you do changes in your container, they will not be stored. So you say that there's ephemeral storage stored in something that will disappear when it's rerun. And this is a feature and not a bug, because you don't want someone to change your container in the middle of somewhere and then you don't know what happened. So each time you start a container, you get the same thing. And if you want to create a container that is different from what you started with, say that you want to have an Ubuntu container with Vim installed, as an example, how would you do that? Well, then you need to tell Docker how to build new containers, because this will be a new object, different from the Ubuntu container that we started before. So you create something called a Docker file. I will use Vim to create the Docker file. And in that Docker file, this is a recipe for Docker on how to build containers. So I need to say that I would like to use the Ubuntu image that we used before. So you say from Ubuntu. Now again, don't focus too much on the exact syntax, but we're starting from the Ubuntu image and we add different things. So now I will add the command run apt update, and then run apt install vim. Save this. Let's look at what the contents of the file is. So from Ubuntu, run apt update, run apt install vim. And then we say docker build. You give it a name. I will give it the name my Ubuntu 20.04. Then you add a little dot. This dot tells Docker to find a Docker file in the current folder. Press enter, and now it's building the container. I did a little mistake, so I need to change the recipe. I go back to the Docker file. I need to add a little y argument there. It's not very important, but I need to do it. So Docker build my Ubuntu, and now we build it. So now it's done. Let me clear the terminal for tidiness, and then we use the same command as we did before, docker run. But now instead of running the Ubuntu container, we run the my Ubuntu container. And now we're inside that container, running the terminal, just as we did before. So let's see, do we have vim installed? Yes, it seems to be working. So that's how you build containers. And we started from the Ubuntu container and added some stuff. Now what you could do is then stack containers like this as much as you like. So we could build a new container starting from my Ubuntu, which may be called my Ubuntu 2, which has Ubuntu, Vim, and some other thing that you want to install. So you can make these Docker files arbitrarily complex. So it depends on what your software is doing. Then you can basically specify anything in this Docker file. Okay, but running operating systems and seeing that you can run Ubuntu or Alpine Linux on a computer is maybe not that exciting. So what is really, really nice with containers is that there's a bunch of pre-built containers in this container warehouse that I talked about before that are built by official teams. Like there's an image for Anaconda. And if you download that, you can get a bunch of data science packages pre-installed. So you don't have to install them on your computer, just run the container and you have all that software directly. And I would like to do that now, but show you a PyTorch container, because we will be using that in the second part of the series, the event. So if I run a Python interpreter on my computer, you can see that I have Python 3.8.10. And if I try to import Torch, so import PyTorch, it's not installed on my computer. Okay, so instead of installing this, I could just say docker run PyTorch/PyTorch latest. Again, don't focus too much on the details here, but I'm starting a PyTorch container instead. I have this pre-downloaded, so it will go faster. Otherwise, it will take a couple of minutes to download it because it's pretty large. So we start it. Now we're inside this PyTorch container. We do the same exercise. We start the Python interpreter. You can see that we have version 3.10.13, so different from what I had on my machine. And then let's try to import Torch. And it just works. And then let's check just for fun. Do I have a GPU on my laptop? I do not have a GPU on my computer, which I expected. So what is nice now, if we instead move over to Berzelius, we could run the same container on Berzelius and have the same environment. And I will show you this now. So now I will share another terminal. This one is now logged in to Berzelius. And I'm in the, oh no. Okay, of course it got, sorry, I need to log in again because when internet died, I was logged out, so that makes sense. So give me a few seconds here. Just need to do two-factor authentication. There we go. So can you still see my my Berzelius terminal, Arnold?
Yes, yes.
Perfect, great. So now I'm inside the login node of Berzelius, which I talked about before. I need to go to a specific folder where I have stored some information. So give me a second here. Now I'm inside the repository that we talked about in the starting of the event. And I would like to go to container demo 1. There we go. So now I'm in a specific folder. It's not very important. And first of all, we need to allocate a node, or we need to be redirected to a node on the cluster. So here you use this interactive command that I mentioned before. And let's request 1 GPU. So now I get sent to this node. I got assigned node number 9. So I was in the login node, I wrote interactive, and then I ended up on node number 9. So here I can check if I have a GPU. I should have one. And it seems like that. Here you can see that I have a NVIDIA A100 GPU, which has 40 gigabytes of memory. Okay, great. So let's see if we can start a Python interpreter directly on the node. We can. We have Python 3.6. And let's see if we can do import torch. We do not have torch. Okay, but so let's install torch. Oh, sorry. Yeah, pip install torch. Cannot use pip. And that's a problem. Maybe we can have pip3 install torch. And maybe this works, or I think it will crash due to a permission error later. But what you can do instead is use this Apptainer thing that I talked about before. So instead of using Docker, we use Apptainer. And we start, I want to enter the terminal. So you say Apptainer shell. You add a little flag to tell Apptainer to find the GPU. And then I write the image that I pre-downloaded just to save some time. So now we're inside the container running the terminal. Let's see what Python version is being run, 3.10.13, which was the same on my computer. And let's import torch. It takes a couple of seconds, but it should work. Here we go. And let's see, do we have access to a GPU? Torch CUDA is available. True. So we have access to GPUs. So we started the same container on my computer and then on Berzelius, and we can see that we have the same environment on both computers, which is what I wanted to show. So now we are ready to move over to Johan, who will do some machine learning and use these concepts, but in a more advanced example. So that was it for me. Thank you for listening. And Johan, you can take over screen sharing.
Thank you, Victor. So I will share my screen instead. Oops. Here we go. Can you hear me and see my screen okay?
Yes.
Perfect.
Okay, great. Thank you. Yes, so my name is Johan Alfredén, and I'm a colleague of Victor's at SciLifeLab Data Centre. And we're running a little behind time, so I'll go fairly quickly here and skip some parts that are not as important. I want to get to the Berzelius parts here. So, but I will illustrate this common workflow working locally solving a machine learning task on local computer. And then we'll move our work over to Berzelius and using containers and our code there to train a model. So let's see here. There we go. So this is our machine learning task. The exact machine learning problem here is not really that important for the aims of this webinar, but I hope that's maybe somewhat interesting to you and hopes that it clarifies the goals of the webinar. So the task here, it's a fairly straightforward classification problem. We'll attempt to train a model that can recognize different categories of common flowers found in the United Kingdom, such as water lily and petunia flowers. We have our data set has some 8,000 RGB images, and we will use PyTorch to train this model. Yes, this data set is quite nice because it's one of the built-in data sets in PyTorch Torch Vision, so it's very easy to download and get a hold of. And then at the end, we'll train a convolutional neural network using PyTorch to work with this data set. So in this first demo, live demos are always kind of a nice adventure, so we'll see how it goes. Hopefully it'll go well. So this first demo here, we'll work locally on my local machine. We'll work in a JupyterLab notebook to kind of formulate a solution to the problem, look at the data set, and so on. Then we'll turn this notebook into a Python script so that we can then move our work to Berzelius and use a container to train our model. So let's jump over to Visual Studio Code. So the first thing I want to point out here's our GitHub repository, Serve Tutorials. This contains all the instructions and code that we're showing in this webinar. So you can download or clone this repository after the webinar and go through it at your own pace if you'd like. In this webinars folder, we have the container demo 1, where Victor has shown his work. And then we have demo 2 in the machine learning task here in the flowers classification folder. So we'll begin by opening up this JupyterLab notebook. So once again, it deals with classification of flower categories. We begin by some settings and some imports of various packages that we need to work with this. We observe that we have at our disposal only a CPU device. And then we download and prepare the data set with different transforms and so on. I'm not going to go through this line by line or anything like that, but here we see it's very convenient to pull this data set. And then we can look at the data set a little bit here, the number of image samples we have. I've reduced this data set a little bit here on the local machine, so it's quite small. We can look at some of the image samples just to get an idea of what we're working with. And then we formulate a solution to this problem that we believe in. So in this case, we're using a pre-trained VGG19 architecture with some transfer learning. And then we're ready to train the model. Now, I'm not going to run this now. I did this yesterday. And with this smaller piece of the subset, took 26 minutes for 5 epochs. And then we can plot some loss graphs and so on. So the idea here is basically just we formulate a solution. We believe in this approach. And then when we're ready, we convert this into a Python script. Here we have this train.py module. And it's very much the same code as in the notebook. We have added this argument parsing here at the top so that for our convenience, so that when we run this locally and on Berzelius, we can pass in we can choose some different options. We can specify number of epochs or learn the learning rate and batch size and so on. So again, I'm in the interest of time, I'm not going to run this, but I did this yesterday and took 12 minutes for 5 epochs with a little different data sets, but a subset. So yeah, let's see. So yes, that was what I want to show in this first demo. So we can go back to the presentation here. And then this next part, I'm going to show a custom Docker file we'll use to build an image that will pull on Berzelius and help to train our model using this train.py code together with our image for training. So let's start with looking at the Docker file. We have this container demo folder. Okay, so we see that this one is based off the official PyTorch image. We specify the root user. Now we'll see on Berzelius in a little bit that will not be usable. We're not allowed to be root. We're going to install a few custom libraries that we need, and then install the packages specified in our pip requirements file. So we can go ahead and build an image from this. We'll see that we're in the right directory with the Docker file. The right Docker build, we give it a name, in this case called custom PyTorch. Oops. And specify the local Docker file. Now that went pretty fast because I've already done this, so it's cached on my computer. And then after this, we could publish this to an image registry, and then check that the package is published, and then pull it onto Berzelius. So I want to point out also that all these instructions of how to do all of this is in this README file. So here we have the Docker build command, how you push it to your favorite container registry. In this case, we're using the GitHub container registry. And then we can verify that the Docker image is published. Now we've done this, we're ready to log into, move our work over to Berzelius. We would begin by logging in using SSH and password and two-factor authentication, as Victor has already shown. Now I've already logged into Berzelius. We can begin by checking our project information to see, for example, how many consumed hours we have, 27 hours, and our current time allotment. So we see we have plenty of GPU time left to use. That's good. We create the solution folder and we clone our code repository here. So we have this worked with. I've already done all this. And then I have two terminal windows open here, just so we can keep an eye on our training in a little bit while we train in the bottom terminal window. So here in the bottom, I will specify interactive GPUs, and we'll grab 2 GPUs with the default settings. Okay. There we go. We see that we landed on compute node 58. Okay, and we can see what happens if we attempt to train. If we attempt to execute our training outside of a container. So I will specify Python 3, try.py. I'll specify just one epoch. Here we go. And we see, okay, we don't have all the required libraries. So we'll attempt to install. No, we will not attempt to install it. Victor already kind of showed you what will happen outside of a container. you'll get a permission denied error. And then instead we will shell into our container. Let's see that we have Apptainer installed and available. Yes. And then we could pull our image using Apptainer pull. It will convert our Docker image that's in an OCI standard format. It will convert that to a Singularity file. I've already done that. So here's our Singularity file. So using this, we can shell into it, enabling an NVIDIA support. There we go. And one very nice convenient thing is here that inside our container, we have access to the entire directory structure and all the files that we had access to outside the container, which is very handy indeed. Now we can check the Python version, 3.10. Where's up here? We have Python 3.6. We can see what user is running. XUALF, so I'm running as my logged in user to Berzelius. And now we're ready to do some training. But before I kick off the training, let's grab our job ID, and you'll see why here in a little bit, using the XQ command. Okay, here we have our job ID. We have one compute job running. And then we'll see that we have our train.py module here. Yes, that's good. So let's start our training. I'll use 12 Upbox just so we have some time to do some monitoring. It will run quite fast anyway. We'll use a batch size of 64. A little smaller learning rate. We'll use 32 workers, mainly to load the data. And then we'll run, let's see, steps. We'll run validation or evaluate our model on the validation set every 200 batch iterations. Okay, so we can now kick that off. And then we can log into the same compute node here. So this can take just a few seconds to load our job onto the GPUs. Wait for that training to kick off. There we go. We observe that's using CUDA devices. And now we're on the same compute node. We can write NVIDIA SMI command. Let's see. I must have specified one GPU in my directive command, I guess. Anyway, we seem to have one GPU using at 74% at this snapshot in time. We can see the training down here below is proceeding quite quickly, already at epoch 5. And the loss is decreasing over time, the losses, and the accuracy is increasing. So we can run the NVIDIA SMI once in a while, see how we're doing. Keep an eye on the GPU utilization of 65%. So I can mention also that this running just 10 epochs on my own local machine using the CPU with the entire data set of the sample takes almost 1 hour. And here on Berzelius, it takes less than 2 minutes. So it's a factor of 50 times faster or so. It's almost complete. Just 1 minute and 36 seconds. Now that's done, we can take a look at the output. It has saved the best performing model as a PyTorch archive file, and then output some graphs, some plots of the loss and accuracy. So now before we end this demo, I do want to point out one thing, that we could have done a lot of this inside a Python virtual environment. This is true. You'd have to install all the packages, PyTorch and required libraries inside your environment, on your local machine, and then on an HPC. Now, even like Victor mentioned, even though it might work on your local machine, it's not guaranteed to work on the HPC because of differences in underlying OS and available libraries and so on. So using containers could be perhaps a more robust way of doing this. And if this makes sense to you, then you're certainly available to try it out. Now, before we end this demo, I want to make sure that we exit not only out of shell, but we also want to exit out of the compute node. You want to release any kind of all the resources that you have grabbed, and keep ticking GPU hours. We can then run the SQ command just to make sure that we have indeed released the compute node, which we have. Very nice. And then we can go back to the presentation. And once again, point out all the materials for this presentation are available in this repository. Here's some contact information for Victor and myself. You're free to contact us after this webinar in case of any questions or feedback. And we want to thank you very much for your attention. So yes, thank you. I'll leave these slides up for just a little bit, just so you have time to write down information and so on.
All right, thank you, Victor and Johan. We got lots of questions during the presentation that were answered and asked and answered in the chat. Does anyone have a question that they would like to voice? Because the questions that I see in the chat have already all been answered, so there is no need to repeat them here. So I see one question: where can we find the recorded video of this presentation? So we typically put the videos on the YouTube channel of SciLifeLab, and all the people who have been signed up for this webinar will get a link as soon as it is published there. All right. I'm trying to see if there is any question that has not been answered yet. Today we have Sean and Somi from the Berzelius support, who have been very good at answering all the questions. Thank you very much, guys. Yes, I see that Daniel is asking and wants to ask a question. So please unmute yourself and go ahead.
Yes, thank you very much. So I was trying to ask this question in the chat. If I use Docker on my local computer, everything works nice, and like the container runs, and inside it knows itself what to install, and it downloads this multi-gig pre-trained model somewhere inside. But when I have to do it on this offline, these supercomputers, I have to make it Apptainer, and that makes things immutable, and everything suddenly stops working. So can you have an example, say, so when you start a container on Berzelius, and then you find out that you need to install something in it, and how to make it work without all these permissions and stuff? Just something simple, like, pip panda in your Berzelius container. Can you do it?
Yes, I can show you right now if you want to, if I understand correctly. So I'll share my terminal right here. So I'm inside a compute node on Berzelius. Let's start this PyTorch image that I showed before. And here I can do pip install pandas. So it installed pandas.
But that's already everything is satisfied.
Yeah,
and like things not writable. So install something for real.
Can you say something maybe by YAML? And that was already satisfied.
Okay.
TOML, TOML. See that?
TOML.
Check them.
I'm loading TOML. So there we go.
So
it should work. I'm not sure if there's exceptions to this, and maybe Chuan or Somi can fill in, but usually you can start the container and then install stuff there, and it should work. I haven't encountered a situation where this doesn't work, but yeah, I'm not an expert on Berzelius.
So the thing here is that when you do pip install, then it will actually install packages to your user side packages directory. Here you can see that, if it's not already there, then it will try to install to your home x_vsum, that directory, but it will not install packages to the system level directories, and it's not limited.
And now if you're using two different containers which want to install like a different version of packages, and because they all go to a local thing, all kind of horrible conflict starts. Can I containerize my installations? So I gave this example with this like H2O GPT because it wants to download these big models inside itself. And when it's in Docker, it kind of handles it by itself, and it's not spilling it out into my folder.
Yeah. Okay. I think I understand. So there's a difference between Apptainer and Docker. So with Docker, you get no volume mounts per default, but with Apptainer, it mounts like your everything I can find inside the container is actually what's on Berzelius. So the container is not isolated by default. And I think perhaps you can redirect the install steps to install it inside the container. So in the ephemeral storage rather than on the machine directly. Is that correct, Chuan?
Sorry, can you say it again? I didn't follow.
Yeah, so if you install something inside a container, when you use Docker, you install it in the ephemeral storage. So it's inside the container, and if you kill the container, everything is gone.
Yeah.
And I think this is the same thing you want to do like with Apptainer, right?
The thing is that I know very limited things about Docker because we just don't use Docker on Berzelius. So I'm afraid that I cannot answer that question.
Okay. But I think it has to do with Apptainer by default mounts a bunch of folders directly onto your host.
Right. So the default mounted directories to Apptainer is, there are actually 3 directories. One is your home directory, and also your project directory, and also the current working directory.
Yeah.
Okay.
And you can add more by, there's this flag called the $B. Then you can mount as many directories as you need.
Okay. All right. I will stop you right there, guys, because we are out of time. Thank you very much, everyone, for participating. This has been a very, very lively session with lots of questions in the chat. There came a bunch of new questions now while we were answering the last one. So those of you who asked those questions and would like to get an answer, please stay and then we will answer them. And everyone else, thank you very much for attending, and we hope to see you in our future events. And thank you, Victor, Johan, Chuan, and Somi again.
Thank you very much, and thank you everyone for listening.